If someone asked where the universe ends, you'd probably say it doesn't. But there's a number in physics that says otherwise. When scientists calculated the mass of the observable universe and asked how big a black hole made from that mass would be, they got a radius almost identical to the age of the universe itself. That number shows up again in how fast the universe is expanding. And that's a problem, because those are exactly the numbers you expect if the universe isn't outside a black hole, but inside one. To understand why this number matters, we need to understand what it means. In 1915, Albert Einstein published his general theory of relativity. The theory described gravity not as a force, but as curvature in space-time itself. Massive objects bend the fabric of space and time around them, and this bending is what we perceive as gravity. Einstein's equations were notoriously difficult to solve. They involved complex mathematics describing how matter and energy warp the geometry of space-time. Einstein himself struggled to find exact solutions. But Karl Schwarzschild, a German astronomer serving on the Russian front during World War I, found one. While stationed in the trenches, he derived an exact solution to Einstein's field equations. This solution described the space-time geometry around a non-rotating, spherically symmetric mass. The solution contained something unexpected, a critical radius. If you compressed any amount of mass inside this radius, something strange would happen to space-time itself. Time would slow down at the boundary. Light could not escape. The object would become what we now call a black hole. This critical radius became known as the Schwarzschild radius. For the Sun, the Schwarzschild radius is about 3 kilometers. The Sun itself is 696,000 kilometers across. So the Sun is nowhere near being a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. For the Moon, it's about 1/10 of a millimeter. The Schwarzschild radius grows linearly with mass. Double the mass, and you double the radius. This creates an interesting property. As black holes get more massive, they actually become less dense. A stellar mass black hole, formed from a collapsed star, crams enormous mass into a tiny space. The average density is incomprehensibly high. But a supermassive black hole at the center of a galaxy, with millions or billions of solar masses, has a much lower average density when you calculate it across the volume enclosed by its event horizon. A black hole with the mass of about 140 million suns would have an average density equal to water. A black hole with the mass of about 11 billion suns would have an average density equal to air. The relationship is mathematical. Density equals mass divided by volume. Volume scales with radius cubed. But for a black hole, radius scales linearly with mass. So, as mass increases, density decreases as the square of the radius. This means that if you had enough matter distributed across a large enough volume, even at very low density, the Schwarzschild radius could theoretically exceed the physical size of the region. And this brings us back to the universe. The observable universe has a radius of approximately 46.5 billion light-years in co-moving coordinates. This accounts for the expansion of space over time. The universe is 13.8 billion years old, but because space itself has been expanding, regions that emitted light 13.8 billion years ago are now much farther away than 13.8 billion light-years. The mass-energy content of this observable universe can be estimated. We know the critical density required for a flat universe from cosmological measurements. It's approximately 8.6 into 10 to the power minus 27 kilograms per cubic meter. This comes from observations of the cosmic microwave background, the distribution of galaxies, and the rate of expansion. Multiply this density by the volume of the observable universe, and you get a total mass of approximately 7.7 into 10 to the power 53 kilograms. Some calculations use slightly different values, around 8.8 into 10 to the power 52 kilograms, depending on whether you count only baryonic matter or include dark matter and dark energy in the equivalent mass-energy calculation. Now, apply Schwarzschild's formula to this mass. The Schwarzschild radius comes out to approximately 13.7 billion light-years in some calculations, or up to 37 gigaparsecs in others, depending on the exact mass used and how you define the observable universe's boundary. But here's where it gets strange. The Hubble radius, which is the speed of light divided by the Hubble constant, equals approximately 14 billion light-years. This is close to the light travel distance since the Big Bang, and it's remarkably close to the calculated Schwarzschild radius for the universe's mass. This coincidence was first noted by physicist Raj Pathria in 1972. He pointed out the structural similarities between the observable universe and the interior of a black hole. The universe has a singularity in the past, the Big Bang. A black hole has a singularity in the future, the point of infinite density at its center. The universe has an event horizon of sorts, the cosmological horizon beyond which we cannot observe. A black hole has an event horizon beyond which nothing can escape. The mathematics looked eerily similar. There is a connection here that goes deeper than coincidence. The expansion of the universe is governed by equations derived by Alexander Friedmann in the 1920s. These equations come directly from Einstein's general relativity, applied to a homogeneous and isotropic universe, one that looks the same in all directions and at all locations on large scales. The first Friedmann equation relates the expansion rate of the universe, called the Hubble parameter, to the density of matter and energy. It can be written in a simplified form. The square of the Hubble parameter equals 8/3 pi times the gravitational constant times the density minus a term related to spatial curvature plus a term for the cosmological constant. For a flat universe, where the spatial curvature is 0, the critical density equals 3 times the Hubble parameter squared, divided by 8 pi times the gravitational constant. Now, consider a sphere with radius equal to the Hubble length, the speed of light divided by the Hubble parameter. Calculate the mass inside this sphere using the critical density. Then, calculate the Schwarzschild radius for this mass. The mathematics shows that the Schwarzschild radius equals the Hubble length if and only if the universe is spatially flat and has exactly the critical density. This is not a coincidence. It's a mathematical relationship built into the structure of Einstein's equations. The fact that our universe appears to be spatially flat with a density very close to critical means that the Schwarzschild radius naturally matches the Hubble radius. But this raises a question. Does this mean we're inside a black hole? In 1939, J. Robert Oppenheimer and his student Hartland Snyder published a paper describing the gravitational collapse of a spherical cloud of dust. This was the first realistic mathematical model of black hole formation. They made simplifying assumptions. The cloud was perfectly uniform in density. It had 0 pressure. It was spherically symmetric. These assumptions allowed them to solve Einstein's equations exactly. What they found was striking. From the outside, an observer would see the cloud collapse until it formed an event horizon. From that point on, nothing that fell into the horizon could escape or send signals back out. The event horizon would mark the boundary of a black hole. But from inside the collapsing cloud, something different would happen. The matter would remain homogeneous. The space-time would remain flat locally, at least until the matter reached extreme densities near the center. The interior could be described using the same Friedmann equations that describe our expanding universe, except running in reverse, as a collapse instead of an expansion. This is where things get interesting. If you take the Oppenheimer-Snyder solution and imagine running time backward, you get something that resembles a universe. The collapsing black hole interior becomes an expanding universe interior. The singularity at the center, toward which everything is falling, becomes a singularity in the past, from which everything emerged. In other words, the mathematics that describes the interior of a collapsing black hole can also describe an expanding universe. The two scenarios are related by a time reversal. This was the insight that physicist Raj Pathria explored in 1972 when he proposed his black hole cosmology hypothesis. What if our universe is the interior of a black hole, embedded in some larger parent universe? From the inside, we would see an expanding homogeneous space. From the outside, if there is an outside, it would appear as a black hole. If a black hole's interior can look like an expanding universe, then what about the opposite? Could an expanding universe look like a white hole? A white hole is the time-reversed version of a black hole. It's a mathematical solution to Einstein's equations that allows matter and light to emerge from a singularity, but nothing can fall in. The event horizon works in reverse. You can cross it from the inside to the outside, but not the other way around. White holes have never been observed. Most physicists consider them to be purely theoretical constructs with no physical counterpart in our universe. They appear in the mathematics but seem to require very special initial conditions that wouldn't occur naturally. But in the context of black hole cosmology, a white hole takes on new meaning. If our universe originated from the interior of a black hole in a parent universe, then from our perspective, the Big Bang singularity would function like a white hole. It's a past singularity from which everything emerged. It's a boundary beyond which we cannot see or receive information. In 1999, Stephen Hawking showed that in certain conditions, the distinction between a black hole and a white hole can become blurred. If a black hole is in perfect equilibrium with the radiation it absorbs and emits, then the mathematical descriptions converge. The event horizon becomes ambiguous. This suggests that the question of whether we're inside a black hole or a white hole might not have a meaningful answer. The interior space-time would be the same either way. Standard general relativity predicts that black holes contain singularities, points of infinite density and curvature, where the equations break down. Similarly, the Big Bang is predicted to begin with a singularity. Singularities are problematic. Physics cannot describe what happens at a singularity. Infinite quantities don't correspond to anything measurable. They represent a failure of the theory. This has led physicists to search for extensions of general relativity that might avoid singularities. One such extension is Einstein-Cartan theory, first proposed by Élie Cartan in 1921. This theory includes an additional geometric property of spacetime called torsion. In Einstein's original theory, spacetime has curvature but no torsion. In Einstein-Cartan theory, both are allowed. Torsion arises from the intrinsic spin of elementary particles, quarks, electrons, neutrinos. In the 1960 seconds, physicists Dennis Sciama and Tom Kibble showed that spin could generate torsion in spacetime, and that torsion would act like a repulsive gravitational force at extremely high densities. At normal densities, even in neutron stars, torsion is negligible. But at densities approaching the Planck scale, torsion becomes significant. It opposes gravitational collapse. Instead of matter compressing to a singularity, it would reach a minimum size and then bounce back. This is called a big bounce. It replaces the singularity with a smooth, non-singular transition. In the 2010s, physicist Nikodem Popławski applied Einstein-Cartan theory to black holes. He showed that when matter collapses to form a black hole, torsion would prevent the formation of a central singularity. Instead, the matter would compress to a finite density, bounce, and then expand into a new region of spacetime on the other side of the event horizon. This new region would be a closed, expanding universe. From inside, it would look like our universe. From outside, it would look like a black hole. Every black hole, according to this model, would spawn a new universe. If black holes create new universes, then our universe was likely created by a black hole in a parent universe. And every black hole in our universe would create its own daughter universe. This leads to a nested hierarchy of universes, a cosmic family tree. Lee Smolin, a theoretical physicist, proposed in the 90s that this process might be subject to natural selection. If the physical constants in daughter universes are slightly different from those in the parent universe, then universes that produce more black holes would have more offspring. Over many generations, the multiverse would evolve toward parameters that maximize black hole production. Our universe, in this view, might have physical constants that are finely tuned not by chance, but by a kind of cosmic reproduction. The strong nuclear force, the electromagnetic coupling constant, the ratio of the proton mass to the electron mass. These values might be what they are because they allow stars to form and collapse into black holes efficiently. This is called cosmological natural selection. It's speculative, but it makes testable predictions. It suggests that we should live in a universe with parameters close to a local maximum for black hole production. Any small change in the constants would result in fewer black holes. The alternative view, which Popowski favors, is that daughter universes inherit the exact same physical constants as their parents. There are no mutations. The multiverse is not evolving, but simply reproducing. This version avoids the problem of explaining how constants could change at a singularity if torsion eliminates the singularity. Either way, the implication is profound. We might be living inside a black hole, and we might be one universe in an infinite chain of universes, each born from black holes in the one before. So how would we know? What evidence might support or refute this idea? First, the Hubble tension. For years, astronomers have measured the expansion rate of the universe using two different methods. One method uses the cosmic microwave background radiation, the afterglow of the Big Bang. The other uses observations of distant supernovae and other standard candles. The two methods give different results. The discrepancy is about 10%, and it persists despite increasingly precise measurements. Some researchers have suggested that black hole cosmology might explain this tension. If our universe's expansion is influenced by the growth or properties of the parent black hole, the expansion rate might vary in ways not captured by standard cosmological models. Second, anomalies in the cosmic microwave background. The CMB is remarkably uniform, but it contains small fluctuations that seeded the formation of galaxies. These fluctuations should be randomly distributed, but there are hints of large-scale patterns. One pattern is called the axis of evil, an alignment of the quadrupole and octupole moments in the CMB that seems to point in a preferred direction in space. This is unexpected in a universe that should be isotropic. Another anomaly is a hemispherical asymmetry, where one half of the sky has slightly more power in the CMB fluctuations than the other half. In some black hole cosmology models, particularly those involving rotating black holes, these asymmetries might arise from the spin of the parent black hole. The rotation would imprint a preferred axis on the daughter universe. Popowski has argued that such features could be signatures of our universe's origin inside a rotating black hole. Third, the James Webb Space Telescope has observed unexpectedly massive galaxies and supermassive black holes in the very early universe. At redshifts greater than 10, these objects appear too mature and too massive to have formed so quickly after the Big Bang, according to standard models. Some black hole cosmology models, which allow for rapid structure formation through bounce mechanisms, might better fit these observations. Fourth, gravitational wave observations. Since 2015, detectors like LIGO and Virgo have recorded gravitational waves from merging black holes. The mass distribution and merger rates provide constraints on black hole populations. If our universe optimizes black hole production as suggested by cosmological natural selection, we might expect certain patterns in the data. So far, the observed merger rates and mass distributions are consistent with standard astrophysical formation channels, but they don't rule out alternative models. Finally, there's the question of rotation. Some studies, including one by Lior Shamir analyzing over 200,000 galaxies, have found a slight asymmetry in the spin directions of galaxies. More galaxies rotate in one direction than the other, particularly at larger distances. This asymmetry is weak, about 51 to 49%, but statistically significant. If confirmed, It might suggest that the universe itself has a net rotation inherited from the parent black hole. None of these pieces of evidence are conclusive. Each has alternative explanations, but taken together, they suggest that black hole cosmology remains a viable hypothesis worth investigating. There's another problem that black hole cosmology might solve. It's called the black hole information paradox. In the 1970s, Stephen Hawking showed that black holes emit radiation. This radiation, now called Hawking radiation, arises from quantum effects near the event horizon. Over time, a black hole will lose mass through this radiation and eventually evaporate completely. But Hawking also calculated that the radiation would be purely thermal, random, and featureless, depending only on the black hole's mass, charge, and spin. It would contain no information about the matter that formed the black hole or fell into it. This creates a paradox. Quantum mechanics requires that information is conserved. The state of a system at one time should determine its state at any other time. But if a black hole evaporates into featureless radiation, the information about its contents is lost. This violates unitarity, a fundamental principle of quantum mechanics. For decades, physicists debated whether information is truly lost in black holes or whether there's some mechanism that preserves it. Black hole cosmology offers a resolution. If the interior of a black hole becomes a new universe, then the information doesn't disappear. It simply passes through to the other side. The information is preserved in the daughter universe, beyond the reach of the parent universe, but not destroyed. This is analogous to the holographic principle, which suggests that all the information about a black hole's interior is encoded on its event horizon. But in black hole cosmology, the information is not just encoded, it's transferred to a new space-time. The arrow of time might also find an explanation here. In our universe, time flows in one direction. Entropy increases. Processes are irreversible, but the fundamental laws of physics are time-symmetric. They work the same whether time runs forward or backward. Popowski has argued that the motion of matter through the event horizon defines a directionality. Matter can only cross the horizon in one direction, from outside to inside, from past to future. This establishes the arrow of time in the daughter universe. The second law of thermodynamics, the increase of entropy, follows from this directionality. The parent black hole, meanwhile, continues to exist in its own universe. From its perspective, the daughter universe is forever in its future, beyond the event horizon, causally disconnected. The parent universe cannot observe or interact with its offspring. When the black hole eventually evaporates through Hawking radiation, the connection is severed. The daughter universe detaches. It becomes independent, a separate space-time with its own destiny. If our universe was born inside a black hole in a parent universe, then, from our perspective, the Big Bang should appear as a white hole, a past singularity from which everything emerged. There should be one, and only one, white hole somewhere in our universe. It would be the connection point to the parent universe, but we wouldn't see it as it is now. We would see it as it was in the distant past, due to the time it takes for light to travel across the universe. The white hole might be beyond the cosmological horizon, the boundary beyond which we cannot observe. If so, we would never be able to see it directly. Or it might be within the observable universe, but so far away that we see only its early state, when matter was still streaming through from the parent universe. Popowski has speculated that some matter from the parent universe could still be entering our universe through this white hole, even billions of years after the initial bounce. This matter would appear to us as an anomalous source of energy or particles, possibly detectable in the cosmic microwave background or in large-scale structure. But the white hole would not be a permanent fixture. If the parent black hole is evaporating through Hawking radiation, the connection between the two universes is weakening. Eventually, when the parent black hole evaporates completely, the white hole in our universe would disappear. The link would be broken. From our perspective, this would happen after an infinitely long time, because time dilation near the event horizon means that events inside the black hole appear to slow down from the outside. But from the perspective of the matter that crossed the horizon, the evaporation would be a finite process. This creates a strange situation. We are in a universe that, from our point of view, is the only universe. But in the larger structure of the multiverse, we are one of countless daughter universes, each born from a black hole, each expanding and evolving independently. There's a deeper puzzle here, one that has bothered physicists since Pathria first noted the coincidence between the Schwarzschild radius and the Hubble radius. The density of the universe is extraordinarily low. The critical density is about 10 to the power minus 26 kilograms per cubic meter. That's roughly 5 hydrogen atoms per cubic meter of space. Most of the universe is empty. Yet, this low-density universe has a Schwarzschild radius comparable to its actual size. This seems paradoxical. How can something so diffuse behave like a black hole? The answer lies in the difference between local and global properties. Locally, at any point in space, the density is far too low for gravitational collapse. A galaxy, a star, even a planet, all these objects are much denser than the average density of the universe. But globally, across the entire observable universe, the total mass is enormous. And because the Schwarzschild radius scales linearly with mass, a sufficiently large volume of even low-density matter can have a Schwarzschild radius that exceeds the size of the volume itself. This is why supermassive black holes can have densities comparable to water or air. The average density decreases as the black hole grows. A black hole with the mass of 1 billion suns would have an average density lower than the core of the Earth. A black hole with the mass of the observable universe would have an average density lower than the air you're breathing right now. But there's a critical distinction. A black hole is not just a region of space with a certain mass to radius ratio. It's a region of space-time from which nothing, not even light, can escape. The event horizon is a one-way boundary in the causal structure. Our universe does not have this property. Light can travel in all directions. We can observe distant galaxies. There's no boundary preventing photons from moving through space. So in that sense, our universe is not a black hole in the conventional meaning of the term, but the mathematics suggests something more subtle. The observable universe might be the interior of a black hole, not the exterior. From inside, the event horizon is not a barrier you can't escape from, it's a barrier you can't return through. It's in your past, not your future. This is the structure of the Oppenheimer-Snyder solution. Inside the collapsing cloud, after the event horizon has formed, the interior space-time is expanding from the perspective of an infalling observer. The singularity is in the future, not the past. But if torsion prevents the singularity, the interior continues expanding indefinitely. From the inside, it looks like a universe. Science requires testability. A theory must make predictions that can be confirmed or falsified by observation. So how do we test whether we're inside a black hole? One approach is to look for signatures in the cosmic microwave background. If our universe originated from a rotating black hole, the CMB might show anisotropies or patterns that reflect the parent black hole's spin. As mentioned earlier, some anomalies in the CMB might be consistent with this idea, but they are not conclusive. Another approach is to study the distribution and properties of black holes in our universe. If cosmological natural selection is correct, we should live in a universe optimized for black hole production. This means the physical constants should be near a local maximum for the number of black holes formed. Small changes in the constants should lead to fewer black holes. Some studies suggest this is the case, but the predictions are difficult to quantify precisely. A third approach involves gravitational waves. If black holes are creating daughter universes, the dynamics of black hole mergers might differ subtly from standard predictions. Torsion effects, or quantum corrections near the horizon, could leave detectable imprints in the gravitational wave signal. Future detectors like LISA might be sensitive enough to test these ideas. A fourth approach is to look for direct evidence of quantum gravity effects. Torsion is expected to become significant only at densities near the Planck scale, which are inaccessible to current experiments. But if torsion modifies the structure of space-time at these scales, it might have indirect effects on particle physics or cosmology that could be observed. Finally, there's the question of the end of the universe. If our universe is inside a black hole, what happens when the parent black hole evaporates? According to Popławski, the daughter universe would simply detach. It would continue expanding independently. The evaporation of the parent would sever the connection, but it wouldn't destroy the daughter universe. This is difficult to test directly, because the evaporation timescale for a cosmological black hole would be unimaginably long. But the theoretical framework provides a self-consistent picture. If we are inside a black hole, what does that mean? At one level, it changes nothing. The laws of physics inside the black hole are the same as they would be in any other expanding universe. The fact that there's an event horizon surrounding us, somewhere in a parent universe, doesn't affect the local behavior of particles, fields, or space-time. But at another level, it changes our perspective on cosmic origins. The Big Bang would not be a beginning from nothing, but a transition from one universe to another. Our universe would not be unique, but one of countless universes in a vast, interconnected multiverse. This raises questions about fine-tuning. Why do the physical constants have the values they do? In standard cosmology, this is often explained through the anthropic principle. We observe these values because they are necessary for our existence. In a multiverse with many different sets of constants, we naturally find ourselves in a universe capable of supporting life. Black hole cosmology offers a different explanation. The constants might be what they are because they maximize black hole production, either through natural selection or because daughter universes inherit their parents' parameters. This is less anthropocentric. It suggests that the universe is not fine-tuned for us, but for black holes. We are simply fortunate that the conditions that allow black holes also allow stars, planets, and life. There's also the question of causality and determinism. If every black hole creates a new universe, and every universe creates new black holes, the multiverse has a recursive structure. Does this go on forever? Or is there a first universe, an ultimate ancestor? Popławski argues that the process might be eternal. There is no beginning and no end, just an infinite chain of universes giving birth to new universes. This avoids the problem of the origin of everything, but at the cost of accepting an infinite regress. Others, like Smolin, suggest that the multiverse evolves over time, with successful universes producing more offspring. In this view, there might be a starting point, a primordial universe from which all others descend. But this starting point would itself require an explanation. These questions touch on the deepest issues in cosmology and philosophy. They are not yet answerable with the tools of science. But black hole cosmology provides a framework for thinking about them rigorously. As of 2025, black hole cosmology remains a minority view in the physics community. The dominant paradigm is still the standard Big Bang model with inflation, described by the Lambda CDM framework. This model fits most observations well and makes precise predictions that have been confirmed. But the standard model has its own puzzles. The Hubble tension, the nature of dark matter and dark energy, the observed large-scale structure anomalies, these are areas where the theory is incomplete or in tension with data. Black hole cosmology offers an alternative framework that might address some of these issues. But it requires accepting ideas that are not yet proven, such as torsion in space-time, non-singular bounces, and the existence of a multiverse. The AD-S CFT correspondence, a powerful result in string theory, suggests that the information paradox can be resolved without invoking baby universes. In this view, the information is preserved in subtle correlations in the Hawking radiation, encoded through quantum entanglement. This has become the dominant view among string theorists, but it does not explain the coincidence between the Schwarzschild radius and the Hubble radius. Loop quantum gravity, Another approach to quantum gravity predicts that singularities are replaced by bounces at the Planck scale. This supports the idea that black holes might not contain singularities, but it does not necessarily imply that new universes form inside them. Recent work on celestial holography, led by Andrew Strominger and others, is exploring whether holographic principles can be extended beyond anti-de Sitter space to flat or de Sitter spacetimes. This research aims to understand the structure of quantum gravity in cosmological settings and might shed light on whether our universe has a holographic description. Meanwhile, astronomers continue to gather data. The James Webb Space Telescope is observing the early universe in unprecedented detail. Gravitational wave detectors are cataloging black hole mergers. New surveys are mapping the large-scale structure of the cosmos with increasing precision. Each new observation refines our understanding. Each new measurement constrains the possible theories. Over time, the question of whether we live inside a black hole might move from speculation to testability. There are many things we still don't know. We don't know whether torsion exists in nature. Einstein-Cartan theory is an extension of general relativity, but it has not been tested at the extreme densities where torsion would become significant. We have no experimental evidence for torsion effects in particle physics or cosmology. We don't know whether black hole singularities are real or whether they are replaced by bounces. Observations of black holes are limited to their exteriors. We cannot probe the interior directly. Gravitational wave observations might eventually provide indirect evidence, but the signals are subtle. We don't know whether information is preserved in black hole evaporation. The AD-S-CFT correspondence suggests it is, but this result applies to a specific class of spacetimes that do not include our universe. Whether the same principles apply in flat or de Sitter space is an open question. We don't know whether the universe is finite or infinite. Observations suggest it is spatially flat on large scales, which is consistent with infinite size. But it could also be finite with a topology that curves back on itself, like the surface of a four-dimensional sphere. If it's finite, the black hole cosmology picture would need to be refined. We don't know whether the Hubble tension is a real discrepancy or a systematic error in observations. If it's real, it might indicate new physics, possibly related to the dynamics of the early universe or the nature of dark energy. Black hole cosmology is one possible explanation, but there are others. We don't know whether the CMB anomalies are statistically significant or just artifacts of noise and selection effects. More data from future missions might resolve this question. We don't know whether the universe is unique or one of many. The multiverse is a theoretical construct, not an observed reality. Some versions of the multiverse are untestable in principle, which raises philosophical concerns about whether they are scientific theories at all. And finally, we don't know what lies beyond the observable universe. If our universe is infinite, it extends forever in all directions. If it's finite, there might be a boundary or edge, but what would be beyond that boundary is unknown. If we're inside a black hole, there's a parent universe outside the event horizon, but we can never observe it or interact with it. These questions define the frontier of cosmology. They are the puzzles that drive research. Some may be answered in the coming decades. Others might remain mysteries far longer. The idea that we might be inside a black hole is both strange and strangely natural. It doesn't change the sky above us or the ground beneath us. It doesn't alter the laws of physics that govern atoms, molecules, cells, or stars. From the inside, a universe born from a black hole is indistinguishable from any other universe. But it changes how we think about the cosmos. It connects the largest structures in the universe, galaxies, clusters, the cosmic web, to the smallest and most extreme objects, black holes. It links the Big Bang to the event horizon. It suggests that the universe is not an isolated entity, but part of a vast interconnected multiverse. The mathematics that describes black holes also describes the universe. The equations are the same. The geometries are related. And the numbers, those strange coincidences between the Schwarzschild radius and the Hubble radius, between the age of the universe and the distance light has traveled are not just accidents. They are hints, clues embedded in the structure of space-time itself. Whether those clues point to a profound truth or a curious mathematical similarity, we don't yet know. The evidence is suggestive but not conclusive. The theory is elegant but not proven. For now, the question remains open. We observe the universe from within, tracing its history back to the earliest moments we can see, measuring its expansion, its composition, its fate. We build equations and models, we test predictions, we gather data, and we ask, are we alone in the cosmos? Or are we one universe among countless others, each born from a black hole, each expanding into its own future? The answer, if it comes, will reshape our understanding of existence itself. But even without an answer, the question is worth asking, because it reminds us that the universe is stranger, deeper, and more interconnected than we ever imagined. And that's the beauty of science. Every answer opens new questions. Every discovery reveals new mysteries. The more we learn, the more we realize how much we don't know. For now, all we can do is watch, measure, calculate, and wonder. The universe unfolds around us, vast and ancient and full of secrets. And somewhere, in the mathematics that describes its structure, in the coincidences that connect its properties, there might be a clue, a hint that we are not just in a universe, but inside one,